All right, welcome to our last video of this unit. This is our 19th video in our 7th unit. This one's called mass spectrometry. You've actually already learned this probably last year. I'm just reminding you because you probably never had this word associated with it. Mass spectrometry is a very, very useful tool, especially if you're interested in determining the atomic weight or the abundance of isotopes of elements. It basically is how we get well, we'll talk about that in a bit. A graph of the intensity of the spectrometer's detector signal versus ion atomic mass is called a mass spectrum. Now, these look a lot like photoelectron spectroscopy, by the way. For example, chlorine has two main isotopes, and 37. That's awkward. Sorry. That should not be 37. So, chlorine has two main isotopes, 35 and 37. And basically what it is this would be the intensity, and this would be the atomic mass. Okay, more so it's giving you the actual mass number of this. And so what we'd see is that chlorine 35, chlorine 37. You could actually then get an idea of this being, I think, like 49%, and this being like 51% of the total height. And then you get an idea of the actual atomic mass of chlorine. Typically, they give you the numbers. You don't really have to estimate it. But again, this whole thing would be called a mass spectrum. So analysis of a mass spectrum gives both the masses of the ions reaching the detector and their relative abundances, which are both obtained from the signal intensities. Kind of just already showed you that. So it's useful again for seeing how much of what type of isotopes we have. In modern times, this is used extensively to identify compounds, analyze mixtures. Basically, you can throw things in a mass spectrometer and get an idea of what's in it, which is a pretty useful tool. It doesn't quite work maybe as well as we'd want to at times, just because you can't quite throw a school desk in there and to tell you, oh, here's all the type of metal and the rust and stuff. But with certain compounds, they can give you an idea of actually what percentage different compounds are composing it. Okay, it can also help determine the actual molecular structure of a newly synthesized chemical. If you work in a lab and you make something and you're saying, oh, what is this? What did I do? It can give you an idea of actually what's in there. Okay, it also, one of the biggest parts you got to realize is it can effectively disprove part of Dalton's theory. Now, Dalton's theory basically stated that every atom of every element is identical. I've already told you that's false because of isotopes, but mass spectrometry is actually what proves that false. With mass spectrometry, we can clearly see the existence of isotopes. I already showed you chlorine. They were both chlorine. They were just different actual mass numbers being detected by that detector, which means they're atoms of the same element, which means same number of protons, but different number of neutrons. So, using mass spectrometry, let me show you basically what we're doing. A scientist deduced that a sample of carbon contained two isotopes, carbon-12, carbon-13. There's normally carbon-14, but in this example, we're just not really caring about it. If the exact weights are given below, along with their respective abundance, calculate the average atomic weight of carbon in the sample. Let me show you what it's saying, and then give you a few minutes to try it. We're saying basically 98.9% of this sample has an exact weight of 12.00000. Okay, kind of exact, but okay. And 1.1% is this. And I'm saying basically what's the average atomic weight. It's called a weighted average. Spend a few minutes. Good luck. Come on back in a bit. All right. Now that you're back, very simple. Our percent abundance is 98.90. In decimal form, this is 0.9890. Remember, I don't have a stylus. Well, you didn't know that. This would be 0.0110. All we do, 12.0000 times 0.9890 0.90 plus 13.003355 times 0.0110. Yes, you need all the numbers. If you didn't need them, they wouldn't have given them to you. When you multiply those out and add them together, you get 12.011. 0, technically. All right, that's your answer. And that's really all you do. All right, here's the atomic weight for silicon that I'm asking you to find it. There's your mass numbers. More so with those mass numbers, here's the exact weight they found. Here's the abundance. Find the average atomic weight. All right, multiply that out. You get 28.0855. Let's see, we need 6 numbers, 085509. Okay, that's your answer. Not very hard. Again, you're just multiplying basically the weight by the percent abundance. If you don't like converting these to decimal, you can multiply this times this without changing it and then just divide by 100 when you're done. That'll get you the same answer. Just make sure, by the way, that your answer is somewhere above the smallest one and below the biggest one. If that's not true, if somehow you got 30, we have an issue. Or if you got, 2,800, you may have forgotten to divide by 100. You should always get somewhere above the smaller and below the biggest. Okay? Have fun, and thanks for watching.